Hello, everybody. I'd like to welcome you to this month's webinar, Applying an Anticipatory Approach to LCA. Those of you who were lucky enough last month to hear Valentino Prado give you Anticipatory LCA 101, we're here to round things out with Lise Laurin, who's not only a pioneer in sustainable return on investment and life cycle assessment. She's the founder and CEO of our EarthShift Global and has used these methodologies for nearly 20 years to support North American industry's efforts at sustainability. So without further ado, I'd like to welcome you, Lisa.
Thank you, Holly. So I wanted to follow up Valentina's webinar, and if you didn't see it, that will be posted here shortly, and so you'll be able to go onto our website and take a look at that. And so today we're going to be looking at how do you apply the anticipatory approach. I've been using LCA to look at new technology, or trying to, since we started. And it's been difficult. So it's been wonderful to see the research that's gone into the anticipatory approach and follow that through time as each piece has come available to us. We've been working at applying it, and I'll kind of give you some of that history as we go through this discussion. As Valentina showed you, there are different pieces of the anticipatory approach, and it kind of focuses around this actual process development and performance evaluation, the actual development process. And I think it's really important that that process is integral to the LCA process, because it helps you understand the constraints that we have on the LCA. So one of the things that we'll look at today is the scale-up modeling, that when you're looking at pilot scale, for example, you're not going to have the same impacts that you might have when you're at production scale. We're going to look at structured scenarios. How is the future going to change, and how does the product adapt through the change? We can bound the analyses, and we'll look at a little bit of that. Valentina talked a little bit about how characterization factors can be developed if you don't have them for your product that you're developing. Stakeholder engagement. Stakeholders can help us understand where are the critical characterization factors, the critical environmental impacts that we want to look at, and how important each one of those is. But it's also, they can also help with functional unit selection, and we'll look a little bit of that today. And then the multi-criteria decision analysis. I actually don't have anything on that for you today, but we'll be looking at that in a future brown bag webinar. So if we look at this and then move a little to the more simplified model that Valentina provided, we're going to be focusing on that technology model and the social context today, just as she did, as these are the things that you can pretty much apply right now if you're developing new technology. So we're going to be looking at this exploration phase. We're going to be looking at scaling up, reducing impacts, looking at a feasibility test, and understanding that the world is changing, and how do we look at that. And then we'll also look at the social context, as I said. So the first study that we did applying what was then called dynamic LCA, I heard Eric Williams talk about it at the ISSST conference a few years back. We were looking at growing algae for biodiesel production. And so we were looking at ponds. We had real data from ponds that were growing algae for dietary supplements. Now, those ponds were producing in volume for dietary supplements, not very big. And so when the results were really far off from the results that some of the other LCAs were showing, I sat down with the researchers at Sandia and said, let's look at what this could look like if we scaled it up. We would have bigger ponds, we would have bigger pumps, and that would improve the efficiency of this system. So we looked at scaling the pond sizes, scaling the paddle wheels and the paddle wheel energy. We looked at scaling the centrifuge size and energy, and then looked at what that would do to the study. The other things that we considered algae with a higher oil to biomass ratio. The algae that we were studying for dietary supplements wasn't an algae that was chosen, or certainly not modified, for having a high oil to biomass ratio. So we looked at what that would do. We looked at a different energy grid, different allocation methods, and we found that that grid energy and the oil to biomass ratio were making the biggest difference in the global warming potential. So you can see that with US electricity, as opposed to the baseline electricity, impacts went up pretty dramatically. If we change the oil to biomass ratio, we could actually change the results again pretty dramatically. So that was the first time that we used anything like the anticipatory LCA. In the end, we were able to get values that were looking quite similar to the other studies that were out there, but we also really hit upon some of the difficulties that people have been encountering in algae biodiesel. That if you have a small system, it's going to be hard to get the values up. It's going to be hard to make it cost effective, let alone environmentally preferable. That we need to have high oil to biomass ratios, that even though we were bubbling the ponds using the exhaust from a coal-fired power plant, that in fact we really wanted to use something cleaner than coal-fired electricity to run those pumps. And so, are you going to bring electricity from someplace else to bubble those ponds? It really pointed out a few of these tricky bits, if you will, with algae biodiesel. We also worked with a small company that was looking to develop hydrogen from natural gas, but reducing the greenhouse gas emissions drastically from steam reforming. And when we put in their preliminary data from their lab scale, we found out that in fact it had higher GHGs than the steam reforming, higher global warming potential emissions. And so we wanted to see, okay, what did they need to do to get it to a point of equivalency? So where did they need to go to get to their goal of being a lower carbon process? We wanted to look at feasibility. Could that be done? Then, in fact, what happened was they considered the feasibility of actually dropping the energy consumption, because that was what was holding us back, down to the point where we showed the equivalency. They went back and did more R&D, and then they shared the data with us again. We modeled again. Did we get there? What else had changed? And so this was a whole process that we did with them. Turned out to be a very valuable exercise, because if they hadn't known what that crossover point was, they might have moved into production too soon, and then later on found out, we're not there, we don't have a product. So this way they were able to improve the processes they needed to before they scaled up, and it was more expensive to do that work. For the same company, we looked at combining the carbon dioxide from coal power again. This is another potential sequestration of emissions from a coal plant concept. What if we combine that with natural gas to create feedstocks? Feedstocks that could be used to make plastics or do other things. So the first function was to sequester carbon. The second function was to create those feedstocks. But when we looked at the natural gas that needed to be input, and we did this through the LCA, for that functional unit of 1 kilowatt hour of coal power, we found out that the natural gas could have on its own created through a nice cogen system, really efficient system, it could have generated 9 kilowatts of electricity. So even though this was feasible and yeah, we could do it, it was kind of like building well, in fact, it would have been more effective to build a natural gas facility next to it, just get rid of the coal, and you would reduce the emissions a lot faster and a lot easier. So it was a very quick assessment of this potential use of their technology that really quickly showed them, don't go here, put your efforts elsewhere. Switching gears a little bit, we have been working with OTR Wheel Engineering and Green Carbon, their subsidiary, on a tire recycling program. OTR Wheel sells off-road tires and wheels, and their clients were asking them, how do we handle these at end of life? They're a real problem for us. And tires in general are a real problem for folks. We've got 300 million scrap tires per year just in the US. While there's some kind of a market for them, they're downcycled, and then a lot of them are either stockpiled or landfilled. And those big pieces are a big problem. So the folks at OTR joined up with the folks at Green Carbon and developed a new process to recycle those tires. And before they went to market with that, they wanted to understand, is this a good solution? And so they came to us to help them with that. So if we look at their process, we're taking some electricity and some natural gas along with scrap tires and the big tracks from the earth moving equipment, for example. And from those creating 2 fuel feedstocks, packaged carbon black, steel scrap, and a process gas. This process gas is actually a fairly high energy gas that then they burned to complete the process. So the process is definitely heated. It's kicked off with natural gas and then use that process gas to keep it going. So we looked at this, and of course there are some emissions from that combustion of the natural gas and that process gas, a little bit of wastewater going to treatment there, but it's a pretty cool process. And in fact, the links that are part of those big tracks, those come out of the process clean enough to be reused directly in new tracks. So as I said, really cool process. So we looked at it from a bunch of different perspectives, and I'm going to show you the different perspectives, although the anticipatory part, in a way, is looking at where were their big impacts coming from. So here we're looking at this process as a disposal service for waste tires. So our functional unit is the disposal of so many tires or so many tons. In fact, it's a megaton of tires. Sorry. And so we'll see here that in human health, ecosystems, and resources using the recipe method, that in fact the natural gas coming in is actually one of the biggest impacts they have. Everything below the line here is a benefit. So not only are we getting rid of tires, but we're also producing all this great stuff. And so in this case, that was looked at as a benefit, that you didn't have to produce those things through conventional methods. So as I said, big hit here is that natural gas. We looked at it then as a method for fuel feedstock production. The fuel feedstock that they are producing has a bio-based content because all of those tires have some natural rubber in them. And so there is some fossil, and it's a mixture of fossil and bio-based fuel feedstock. And so again, we've got some benefits from avoided landfilling of tires and the avoided steel, and then the packaged carbon black. But we also have, again, this natural gas in here, and you'll see why that was important in a minute. If we just look at the operating perspective here, and so we're not looking at what's being produced, we see that that natural gas is, and now we're looking using Tracy as opposed to recipe, we see that it's still a pretty big contributor. One thing that I'll point out here, the capital equipment is also a pretty big impact here. And this is something to really pay attention to when you've got big capital equipment doing processes like these. They can actually be something to be looking at. So please keep that in mind as you're doing your LCAs, that you do want to make sure that that capital equipment isn't a big impact, a big part of your impact. But if we ignore that, we do have some electricity that's an impact, but that natural gas is certainly showing up here. So the next step that they did was they were able to eliminate the use of natural gas because they actually produce enough of this process gas to run the entire process and still have a little bit left over for the next one. Because they have a little bit left over, eventually they're going to end up to the point where they can actually produce some electricity or sell that excess energy for use elsewhere. So that would be another benefit. So that's where they are now. They have they've done that piece, and we're now in the process of doing another LCA. But here, that LCA at the point of pilot scale, if you will, allow them to really narrow in on what can we do to improve this process. So a very practical application here. So the next study that I want to talk to you about, or work that I want to talk to you about, was with HP. And here we were looking at their brand new 3D printing technology. And I'll show you in a minute. HP has a little bit different way of approaching their 3D technology. And they wanted to see, how does it compare with injection molding? They're looking at putting this technology not in libraries like a lot of the 3D printers, not in homes, but these are really for larger scale production, not for one-offs, but for multiple offs. And so they were looking at working with the automobile industry. We did partner with an automotive company, and then we looked at producing some parts for them using the 3D technology versus their conventional injection molding. So as I said, it's a little bit different technology. You have a bed that can hold multiple parts. The bed then has a layer of material put down. In this case, it was nylon 12, so a little bit of nylon 12 resin. Then some agents were applied. An infrared lamp is applied to fuse where the resins are applied. And then another layer is put down, and the same thing happens again. So it's still a layer by layer process that allows you to make really cool forms. but it's making multiple in one pass, and so it's a pretty efficient system compared with many of the 3D printing systems. So the explorative conditions that we looked at, we also looked at the social here, so we'll get into that. The first thing we did was we looked at how many parts could we make before injection molding became the preferred technology. And so you'll see here in the dotted line, that is the injection molding impacts. In injection molding, we have to make a mold. And so until you've got impacts of the mold amortized across enough products, it's dominating these impacts. And you'll see that this starts to flatten out as the impacts of the mold go down to essentially nothing per part. You'll see a couple, so that then we have the 3D printing process as it exists today, pretty stable across all the different volumes of parts. You'll see in here a couple of fuzzy balls, 3 of them actually. That's where there is uncertainty. So here at the 1500 part level, there is uncertainty as to whether the 3D printing process at its baseline is uncertain in comparison with the injection molding. Then we have in this bluish circle, we have an area where it's the injection molding versus 20% less electricity use with the injection molding, where that's uncertain. That's at 3,000 parts. That 3,000 parts is also uncertain when we use 40% electricity. Now, when I say it's uncertain, what does that mean? It means that at this point, if the injection molding, or sorry, the 3D printing process could reduce its energy by as much as 20%, with the information that we have today, our background data, our data quality, those two processes are indistinguishable in the area of greenhouse gases. It turned out it was indistinguishable in actually most of the categories right around there. So, you know, that's really interesting for HP. They understand, well, you know, we've got some advantages in comparison with injection molding. These parts can be customized per car if people want. There's a lot of flexibility there. And so they can say, well, we're equivalent to at that point. Below that point, well, actually right now, below the 1500 parts, they're actually better. So for really low volume cars, and yeah, there are still some specialty cars out there that have lower volumes than 1500, they have a benefit, and that's really cool. At 1500, they're basically equivalent. So that was really interesting for HP, and really gave them a driver for looking at what to do next, perhaps reduce those energy impacts. Now, the next thing we looked at is the capability of 3D printing to lightweight. And so the parts that we were looking at could be lightweighted by as much as 20%. That's what the automotive engineers that we worked with said. And so again, we've got the 3D printing as it stands today in this gray line, and then the 20% less mass in the blue line. I'm seeing a little jag in this line that is an artifact perhaps of my screen. If you're seeing that, it's not really there. And then again, the injection molding is this green dotted line here. So as we look at this, we see almost the same picture that we saw before. The 20% less lightweighting, because in fact these parts were very, very light, didn't make a lot of difference. But we looked at a different part, a much bigger part actually, and wanted to look at what did that show us in terms of lightweighting. And here we looked at this in a couple of different ways. So the gray line is our baseline without the light weighting. The blue line is simply reducing the mass by 30%. And then the black line here is looking not only at lightweighting the part, but what that does to your fuel consumption. And probably not from just this part, but as part of the whole process that automobile manufacturers are doing to lightweight their vehicles and reducing the energy, reducing the overall mass, and reducing the size of the engine needed to move that mass, and all of those together reducing the energy consumption. So we used standard automotive data to look at this. And so what we found here is only with the 30% less mass, we're getting into the area where the 3D printing is essentially equivalent to or indistinguishable from, I should say, the impacts are indistinguishable from the injection molding, or they're less. And so right now today, with that light weighting, with a larger part, the 3D printing is providing a really good benefit. But then if we go into this further lightweighting of the vehicle and what lightweighting this one part might contribute to, it's actually quite a bit of benefit and significant, because we looked at the uncertainty here, and it's really there. It's a real reduction in energy consumption. So all of this information is really valuable for HP. Where do we go with this technology? And if you haven't looked at the HP 3D printing news, they are making big strides with this technology. They're changing on, they're doing a lot of changes. They're adding materials that they can look at. And all of this is being informed by an anticipatory approach to LCA, which I find fascinating, and I think is a really great example of how LCA can inform innovation. Oh, one more thing I forgot to show you here, and this is I did a blog post on this a little while back that hopefully you read. But one of the things that we always like to look at these days is what happens as our grid is changing. All of us are experiencing a changing grid. Most of us are looking at a cleaner grid than we were before in terms of greenhouse gas emissions, particulates, and a lot of other things. And so one of the things we did look at here is how is the 3D printing process going to change as the grid gets cleaner? We were looking at both European and US energy to begin with this part, as there are automotive manufacturers, and a lot of them in both the US and in Europe. And so HP wanted to understand that. But they also wanted to look at wind power. And so we looked at how wind power changed the configuration. So this is with that larger part we just looked at, and you see that the impacts drop pretty dramatically as we clean up the grid. So that was another interesting change. Hopefully it doesn't mean that we go and use more energy as we get a cleaner grid, but it does mean that the 3D process certainly gets better as we go that direction. So that was another piece that was really useful for HP to understand. One of the things that HP wanted to look at was, what if we change our distribution? We did look at that. Wasn't a whole lot of opportunity there from an environmental perspective. However, we did also look at, what if you have a car or a dishwasher, we talked about dishwashers a lot in this context, that you couldn't get a part for. what would happen if you could pull down the drawings and make a part, or your repair folks could make a part? What would happen if that meant you could keep your car or your dishwasher a year longer? And this was something that we did look at putting some boundaries on, but it was something that HP didn't really want to share the results with publicly because it didn't feel like it was robust enough at that point. That we're looking at this. You know, if our functional unit is one vehicle, how do we really look at a longer life for that vehicle? So I think this will be something we may explore in the future, but it's quite an interesting thing to look at. We also looked at HP, at 3D printing in general from a social context. Where are people concerned about 3D printing? And so we did actually an SROI. So we did some of the social screening that the anticipatory approach looked at, but we went further and we actually monetized that. So I'll show you a little of that, but I think the important part for the anticipatory approach is really considering who is affected by this and how are they affected. And what are the social impacts coming, and how do they inform or not inform the LCA portion? We did look globally. We did look at this from a screening level. So if there was an ISO standard on SROI, I'd probably not be able to share this with you. But take it as an academic study and let's move on. And so we did this through, as I said, it was screening. How we did that through just literature research. What do people care about in terms of 3D printing? And so it's not specific to HP, it's not specific to their technology, it's more of a generic screening level study. So we looked at amputees having a better quality of life through the availability of custom prostheses. And this definitely points us toward human health impacts in 3D printing, because you don't want to be improving human health for the amputees while at the same time damaging it through the 3D printing process. Same thing with the better surgeries. Again, we're looking at human health. We looked at products lasting longer, products being lightweighted, these things that we just talked about, and we looked at those from an environmental perspective. We also looked at the potential that there would be more widgets produced. You know, people can now make all kinds of custom things. They can just go to the library and make something. They're going to make more of them. But we also looked at the flip side. And if you look on the HP website, they have a shoe on there. And I have a really weird shoe size. So this one really appeals to me. If I can make a shoe that fits, then I can buy something, it'll last me a long time and I don't have to buy any more. Whereas half the time when I buy shoes, I wear them for 2 weeks and I can't wear them anymore because they just don't fit right and they don't mold to my foot. So it means for me, if I can buy a 3D printed shoe that's for me, I won't have to buy lots of shoes. So that's pretty cool. So we looked at fewer widgets being made because they're actually right the first time. We don't throw as many things away. We looked at the risk that there's design piracy, that people are able to scan a product and make it and not have to buy it from the manufacturer. We looked at what if subsistence farmers in Nicaragua could become inventors and manufacturers, right? Isn't that cool? And that this technology really does allow that, which is pretty neat. And then what about if sculpture became more affordable? Oh. What happens when sculpture is more affordable? Does that mean that we can have more artists? Does that mean we can have more art? what does art do? Well, art makes us happy, and art makes us less stressful. And that, if we're not stressed, we have better health. So it all comes around. So let's look at the impacts. This isn't by stakeholder. This is just by kind of the cumulative of the different scenarios we looked at. And our functional unit here, if you will, was one printer over its life. So we kind of said, oh, well, one printer can help perhaps one farmer and maybe lightweight one product. So we looked at just the output of one printer here. So here's our capital expense to start. This is dollars. I should say that we have dollars here. The light gray line is the total range of the results that we calculate. So the ends of this are really small probabilities. This is our once in 1,000, once in 10,000 probability. The next gray line here is our 90% probability. We have a 90% probability we're going to be within this range, and the very darkest value is our 50% probability. So we're looking at, as I said, capital expense here, fewer widgets produced, more widgets produced on either side, fewer lawsuits, etc. The affordable sculpture, I was really disappointed how small this one came out. And it turned out that the biggest risk for us as a society is this design piracy, and something that we as the society need to definitely look at so that we can use this technology and honor each other. And so we looked also at what if standards were developed to actually minimize that design piracy. And so if I add all my scenarios together, I see that, well, that design piracy is pulling us down, and we don't have a real great return on investment for our 3D printer. But if we minimize that impact of property infringement, that we have a nice positive social return on investment, social and environmental return on investment. So a good sustainable return on investment from that 3D printing technology. So this was really cool. Good to know that when we went to and presented this at ACLCA, they actually came up with a whole bunch more social impacts. So looking at social impacts is something that you might not want to do in isolation, but actually go out and ask people. So what can you do? I want to now kind of move to what you can do to apply an anticipatory approach to LCA. As Valentina said last time during the Q&A, you don't have to apply the entire approach. You can pick and choose what you can do today. Some of the things that you might want to do may be beyond the tools that we have, that you have available to you. And so you may want to just pick and choose the ones that you can do, but get started on it. And there are lots of ways that you can get started on it. So even for mature products, you may want to look at what's the future going to be? What is the future energy mix going to be? What is our future? What are your suppliers going to be doing? Where are your suppliers going to be? Let's anticipate future changes. That does a bunch of things. It means that your study isn't stagnant and only applicable to the past. It means that you can apply this study, the results of this study, to the future. And as things change, understand where you are with your impacts due to those changes. You can always create models with the worst case and best case alternatives for your unknowns. So when you're doing an LCA for a new innovation, something that is just a concept right now, you're just in lab scale, you're just in pilot scale, you may not know all the answers yet. So look at the best case and worst case. If I think about the 3D printing example, we don't know maybe when we're building this machine what resins it's going to work with. Well, let's look at the worst one and let's look at the best one. What does it look like with each of those? Does it even make sense to move forward with the worst one? And for some, like the case of the hydrogen, they didn't have a market if they weren't lowered greenhouse gas. So it's really important that in some cases that you take that into consideration. But it also provides you information. Where do you start? And you can do that with all kinds of things. Look at the best case and worst case. You can also look at what are the concerns with a similar technology. So if you don't want to let the cat out of the bag of what you're doing, and you want to understand what stakeholders might be interested in and what they might be concerned about, look at a similar technology. Look at something that is along the lines of what you're doing to understand where stakeholders are concerned, and always reach out to stakeholders if you can. One of the things that comes up a lot, sometimes it comes up with regular LCAs, but certainly with new LCAs, and particularly when you have new materials or new chemicals that you're working with, you may find out that your emissions are not getting picked up. The impact assessment, that they're not included in the impact assessment methods. If you don't know how to find that out with the tool that you're using, whether or not those impacts are being picked up, talk to your tool vendor. Find out how to do that. It's really important with the new technology that some of those impacts are picked up, because if those emissions aren't getting picked up, you don't understand the extent. Now, if they're not getting picked up, what do you do? Again, we go back to what Valentina said last time. They need to be added to the impact assessment method, and that can be done. There are people who can teach you how to do it yourself. That works best if you can already do risk assessment. If you're not a risk assessment expert, I'm not, and I don't have anybody on staff who is, so we actually pay somebody to do that for our studies. It's not exorbitant, it's very reasonable, and then those materials or chemicals, those emissions get added to the rest of the, to everybody's impact assessment method. So that's a good thing too. So with that, I want to actually close, and one more thing before I open this up to questions. I want to say, when you're doing an anticipatory LCA, you probably don't have all the answers. So you want to reach out to people who know more about what you're modeling than you do. With the algae study that I first talked about, the researchers that I was working with didn't have any idea what the scale up would look like and how the energy consumption might be reduced by bigger pumps, bigger ponds, etc. And so he reached out to an expert who knew, and that was really useful. We have reached out, as I said, to folks who know more about risk assessment and impact assessment to help us with our looking at the impact assessment methods and make sure that all of our substances or our elementary flows are picked up. And if you want help with your goal and scope, reach out to your LCA consultant. Ask them to help you, or talk to your team about it. Don't try and do this in isolation. I would say anticipatory LCA, as much as any LCA, really benefits from that bigger picture that you get. We all get into the weeds really fast, and because that's the nature of what we're doing. Have some help getting you out of the weeds. It's a really good thing to do. So with that, I will open it up for questions.
Okay, Lisa, thank you very much for that interesting talk. I do have some questions for you from people.
Great.
Other than the electricity mix, what would you change in the model to project into the future?
Well, you know, that really depends on what you're modeling. So if I'm modeling, let me think. If I'm modeling, manufacturing a toy, I might want to look at 3D printing and as opposed to my injection molding process. How would that change it? I might look at other materials. What would it look like with a bio-based material if bio-based material would become more available, or a recycled material? Look into the future, what's changing? And you always want to do that when you're innovating anyway. So work with your team that's innovating and say, you know, what do you think is going to change in this manufacturing process, in what's happening here?
Okay, thank you. Where do you find information on technology trends?
Oh, okay. So the internet is where we go. I will look at trends, or history is another one to look for. You want to look for the thermodynamic limits as well when you do that, because if you look at trends, sometimes they'll get you to a place which isn't actually feasible, physically feasible. And so it's good to look at, as I said, what intrinsically can happen with the materials before you go further with them.
Okay. Um, can you please speak about how anticipatory LCA is conducted differently from attributional LCA?
So in a way, you could think of it as an attributional study. We're doing a lot more scenario analysis, first of all. We look a lot more using uncertainty. So we're not applying this as what did happen or what is my supply chain today, but we're kind of doing an anticipatory on a future that doesn't exist a little bit, right? We're making stuff up along the way. And when I say making stuff up, I don't mean that we're creating things out of nothing. What I mean is we're putting realistic boundaries on our energy consumption and what kind of materials we're going to use. And we're projecting into the future and saying, what could happen in the future? And we're modeling that, and we're modeling best case, worst case, to see where are the bounds? Where does the answer to my question, is A better than B, which is often what we're trying to do, where does the answer change? In the case of algae-based biodiesel, where we were looking at where is the point at which algae biodiesel is better than petroleum diesel? What do we need to do to get there? Do we even have a clear path to get there? In the hydrogen study, we were looking at where do we get better than the conventional hydrogen production process. And again, the 3D printing, the tire process was a little bit different, where we were, current technology isn't that great. So we were more looking at, and part of our study was, okay, let's produce some biofuels. Let's produce some carbon black. Let's make this a production process and see what happens. Let's produce steel. So I'm going off a little bit on a tangent here, but it's more like it's taking our traditional LCA and just really broadening the perspective and the boundaries. And hopefully that answers your question. If not, ask again.
Okay, thank you. And how do you assess emissions of new chemicals using the anticipatory approach?
Right, so that was what I was just talking about. So new chemicals, now there's two pieces to that. The first piece is the inventory. And I was just introduced to a new tool that Sang-Won Soo has been developing at UC Santa Barbara and the Bren School there, and it's called the CLICK tool, CLICK, I think it is. And that is an interesting tool that helps. It uses artificial intelligence to predict the life cycle inventory and impacts for new chemicals. As far as emissions go, each of the impact assessment methods has a way to show you how to calculate the impacts of any new emission. And so if you know how that's done, you can calculate yourself. You can follow the emission through the different fate transport models, etc., and put it in yourself. If you are not familiar with that, as I just said, you can ask someone who is a model developer or impact assessment method developer to do that for you. As I said, it's quite reasonable and something that we do. But you want to do both those. If you can find a good proxy for the life cycle inventory, then I think, in fact, the CLICK tool could be a really interesting option. And on the other end, the adding it to your impact assessment method for the emissions is really important as well.
Okay, thank you. How do you find out what stakeholders care about?
So, as I said, with the 3D printing study, we looked online for, what are the issues with 3D printing. So we looked at that. But your best bet is to do some stakeholder outreach. And I think a good place to go to for stakeholder outreach are the nonprofit groups, the NGOs that are interested in your industry. Reach out to them, find out what they're interested in. Talk to politicians, talk to people in the street, talk to your customers, talk to all those folks and find out what their concerns are, what are their hotspots. If you can follow through your supply chain up and down and understand where people are concerned, that's a great place to go, as well as the NGOs. Great questions.
Okay. And last question that I have, and I'm welcoming any more if people have them, is where did you find out about anticipatory LCA?
So yeah, so I mentioned a little bit about the ISSST conference, which, by the way, is coming up in June. And that's really where I've watched the development of the anticipatory approach come through. So I think, in fact, the first time I saw any piece of it was a long time ago. I saw Tom Seeger present at a material science conference, I believe it was, on stochastic weighting, which is a part of the anticipatory approach that we haven't actually gotten into yet. So that was the first piece that I saw, and that got me curious. And then a few years later at the ISSST conference, I saw Eric Williams present on what was then called dynamic LCA, and that's been pulled into the approach. When Valentina came to work for me as an intern years back, she was working on her own contribution to the anticipatory approach through the SMA, and so I got firsthand knowledge of that through Valentina, and she did that also with Tom Seeger at Arizona State University. Tom also was working with Ben Wender and his other students on the fuller anticipatory approach. Valentina was also part of that effort. So it was a broad effort with a number of students contributing under Tom, and through the ISSST conference, I've been able to follow that over the period. So I do put in a plug for that conference as a place if you want to follow the latest and greatest of what's happening, listen to some of the greatest thinkers in this space that are moving us forward. Highly recommend the conference.
Great. Thank you very much. And I will be ending this webinar, but I wanted to invite everybody to our next webinar next month, which is with a woman by the name of Wakuna Galega. And the title is a little daunting, Elucidating the Role of CO2 in Type 2 Methanotrophic Growth and Polymer Synthesis. So stay tuned for that next month, and thank you everybody for participating, and we'll hope to see you later. Bye-bye.